So we're going to be looking at elementary reactions versus like mechanisms a little bit. And so an elementary reaction is going to be a single step. In this elementary reaction, we're going to see that our rate expression would be rate equals K, and that would be equal to A times B. And I'm going to zoom way in so that I could put coefficient there. What? You mean all of those rate expressions we calculated, we could have just used the coefficients on the reaction? No. We don't know if it's an elementary reaction or not just by looking at it, okay? Because it could be an overall reaction. We still have to calculate those unless it specifically tells us it's an elementary reaction, or if we know it's part of a mechanism, like we see it as a step in a mechanism, okay? So again, if we wanted to figure out what those exponents are experimentally, you'd have to do a rate expression problem or a differentiated rate law problem, okay? If we know it's an elementary reaction, we can use those coefficients to give us the exponents. Our overall reaction is going to be the sum of all elementary steps. I gave myself more room. And I'm putting EXP there because those have to be experimentally determined. And again, when we're looking at these reactions, we just see a balanced equation. We can't tell if it's elementary or if it is an overall, okay? And so we got to treat them as all overall reactions unless they give us a clue that it's elementary, okay? Now, when we talk about a mechanism, this is going to be a series of reactions. And in fact, those are going to be elementary reactions. And these go in order. So Hess's law, we did not have to have those in any particular order. We could just add them together. But here we are looking at the elementary reactions in order, like process 1, process 2, process 3. We're going to see that it may have rates out to the side for us. It may say fast or slow, but it's going to tell us kind of how fast we're going. Our intermediates are going to be products formed, then used. So an intermediate is something that's made, but then we end up using it later, okay? So it's going to show up as a product, and then later on in the mechanism, it'll show up as a reactant. Overall, it is not participating. We could consider it a spectator. We call it an intermediate because it is actually participating in a reaction, just not the overall reaction. Okay, and so here we have a mechanism, just a very basic mechanism, okay? And so I want to take a look here and let's find our overall reaction here. Making sure I can cancel out. And it wants us to write the rate law for each elementary reaction, okay? So that would be our differentiated rate law. So rate equals K, and I'm just going to say K1 because this is going to be the rate constant for just the first K, first reaction. And what is our reactant here? A, and we've got two of them. It does say it's elementary, so that means my exponent would be 2. This would be a second order reaction. So for our second step, we had two reactants, C and B. And those are both 1s, so that would be raised to the first. This is still a second order reaction, but it's first order C and first order B. I attempted to do different colors for y'all, but
and it's still second order because 1 plus 1.
1 plus 1 is 2. So the overall order for the reaction is 2. And then it looks like here we would have D and B, both to the first, which makes our reaction second overall. And 1 plus 1. Nothing. I'm sorry.
Did you ever have like the first one be 1, the second one be 2, and the third one be 3?
You could.
You just have to like average them together? Or
Like in terms of the order of the reaction?
Yeah.
Yes. No, you don't have to average them together. What you would do is you would have to, and we're going to learn, we write the rate expression for what we call the rate determining step. It's the slow reaction. So the slow reaction determines the rate of your reaction. Just like on a relay, the slow leg of your relay kind of determines how fast your relay can go. Okay. All right. So questions about what an elementary reaction is? Are you feeling pretty good about what an elementary reaction is? Feeling pretty good about what a mechanism is? What it looks like? Can we add the reactions together? Okay.
Will the order always be 2 in each mechanism?
No, it will not. And Olivia was asking as well, if like you could have different orders, and you can. So they can be all different orders, and we're going to use the slow one to determine our rate expression. Okay, and so here we've got another practice problem on this next page. So I'm going to have you try it, and then we'll check. All right, did we get rate is equal to K times NO concentration and Cl2 concentration?
Yes, ma'am.
Both of those first order, second order overall.
The first order, second order.
Like they're first order in the first reaction. Like NO is first order, Cl2 is first order, and then overall it's second order. Okay. Our intermediate is NoCl2 because it is made. Notice it's made, and then we use it up. Okay. And then our overall reaction, we should have 2 nitrogen monoxides, a chlorine, and then 2 NOCLs. Okay, good. Don't worry, we're not done with mechanisms, okay? But we are going to talk about the collision model or collision theory. All right, so the collision model is going to talk about how things bump into each other, okay? And so it says that in order for an elementary reaction to make products, the reactants must collide. You guys are going to hate me for this. Successfully. But we do have successful collisions down below, so we're going to talk about that. So in order for it to collide and for these particles to actually stick, okay, and make, this is what we're assuming here is that we have these particles, they collide, they form almost like an intermediate, we call it a transition state, and then they break apart, okay, into the new products. So like they collide, they rearrange, break apart, new products. In order for that to happen, one, we have to have the correct orientation. And we're going to have sufficient energy. So they have to hit in the perfect way so that they can form the activated complex, and then, or the transition state, either one. They're synonyms there, activated complex or transition state. They've got to hit correctly so that they can stick for a brief instant, and then they've got to have enough energy in order to stick together, okay? So I want you to think about like a car wreck. Is it possible to hit somebody and then your cars stick together? It's possible, but you got to hit it just right, correct? Okay, and so that's kind of what we mean by correct orientation. And then enough energy, again, you might have to have enough energy to make it stick too. Because like if you hit a car with enough force, you could very easily lock bumpers. Like it could get stuck on the license plate or the truck hitch or trailer hitch or whatever you've got there, okay? But there are possibilities there. And again, not the best analogy in the world, but I think we kind of understand with that. So with this, we do look at our Maxwell-Boltzmann distributions. And again, here we're not necessarily looking at our speeds, but we are looking at our kinetic energy, okay? And so here we've got our different amounts of kinetic energy. And this here is what we consider the energy required to achieve the activation energy. So we're looking, activation energy. I've heard that before in this class. What is activation energy?
The energy needed to activate.
I was hoping you would say that since I just gave you successful or collide successfully. It is going to be the energy to activate. What are we activating though?
The reaction.
The reaction. So it's the energy required. I like to think of it as our startup capital. It's the amount of energy required to get the reaction going automatically. And in this graph, we're looking like here's the activation energy right there. Okay. And so then it'll tell us like how many particles are going to have that amount. So the area under this curve here, this area, which the area under a curve is an integral, but this tells me the number of particles I have because we've got like there's 5,000. These are all number of particles on there. So the area under that curve for that amount of energy is how many particles we can actually see to have a reaction. Okay. Our purple one over here, are we going to have as many particles react? No. Which one would have a greater rate of reaction? Yeah, the red one. The more particles, right? Rate. I'm going to put higher rate. Again, if we have more particles that actually can collide, our reaction's going to take place faster. Okay. Y'all, if we increase the temperature of our reaction, will the rate go up or down?
Up.
Up. Why?
Because they get faster.
Uh-huh. They're moving faster.
And they collide more.
We're going to collide more. And if I have a higher temperature, I have a higher kinetic energy. Higher pressure, which is our collisions of our gases, right? So we should have more collisions. These particles are moving faster, but they should have more energy because they are moving faster in order to surpass their activation energy, okay? So that is why when we increase temperature, the reactions go faster because there's more kinetic energy available for it to react. All right. We kind of just went over. Let me come back to that. All right. I'm going to come back to that one in just a second. So here, which of the following best helps explain why an increase in temperature increases the rate of chemical reactions? Let's see if we can summarize that and pick out. Did we say D?
Yes.
Yes, very good. Okay, I'm going to annoy you, but let's go back and fill this in. Y'all, I knew two of them, and I was like, what is the third one? Why? Where are they getting three for this? Because we had already talked about sufficient energy. They have to have the correct orientation. And none of that works if they don't hit each other. So that was the first one. And again, I just wanted to double check what they were having for that third one. I guess technically you do have to have a collision in order for there to be a chemical reaction. So thank you for your patience on that brain fart. Okay. I'm going back over here. Again, our activation energy, we've already defined it a couple times, but let's do it again. Let's see what kind of definition you can come up with for activation energy. How would you describe it? We will eventually. I just wanted you to talk about activation energy.
Okay, I didn't see that part.
Yep, no problem. Loving it. Love it. Love it. All right, I'm loving the definitions. Looking good. Okay. All right. So again, pretty much the energy that's needed in order for a reaction to occur, like to get it started and going. Um, Next one, this reaction occurs in a single step that involves the collision between NO and nitrogen trioxide. A scientist correctly calculates the rate of collisions that have sufficient energy to overcome the activation energy. The observed reaction rate is only a small fraction of the calculated collision rate. Which of the following best explains the discrepancy? So again, he's calculating the reaction rate in terms of significant energy, but that is not what he's seeing experimentally. Experimentally, he's seeing a slower rate. What is he forgetting? It's not temperature. The temperature will help you reach activation energy faster. What do particles have to have in order for a reaction to occur?
Activation energy.
We got to have enough activation energy. We've got to have enough or collisions, and then those collisions have to be in this correct orientation. So if we're colliding, we know he correctly calculated the rate in terms of having enough activation energy, but he forgot to take out the collisions that weren't in the right orientation. And so our letter choice here would be B.
This was a hiccup. Yes, ma'am. Thank you.
Yeah, no. All right, let's take a look at this next one. Ooh, wait, before we do that, what does it mean when the problem says single step? It is an elementary reaction. All right, so let's see here. We've got in an experiment, a student studies the kinetics of the reaction. It wants us to use the data in the table to do the following. Determine the order of reaction with respect to S8. Those are called flowers, sulfur flowers. They make rings and it looks like a little flower. Instead of a diatomic, it's an octatomic. Okay. Or an allotrope, another allotrope of sulfur. An allotrope is an element that has a different number of atoms attached. So like oxygen and ozone are allotropes of one another. Like diamond and graphite are allotropes of carbon. they're both made of carbon but have different structure. To determine the order of the reaction. All right, what type of rate equation is this screaming?
Rate expression.
Rate expression. I see a table when I see initial, and then initial rates. And so let's go ahead and I'm going to have you guys calculate what the order is with respect to S8. All right. Just out of curiosity, did we get first order for S8?
Yes.
Okay.
I
Question.
really
Didn't know that you did.
Why'd you change like 0.699 to 6.99? Just so it'd be easier to divide.
I didn't mean to. I really didn't mean to. No. There we go. So I'm noticing here that I've got 0.3 divided by 0.1, which is 3. So that's where I'm getting the 3 to the n. I did that math in my head. And then here I've got 2.10 divided by almost 0.7. Or if I move my decimal places over, that's 21 divided by 7, which is 3. And so that's how I'm getting my first order for S8. Then down here on E2, it wants us to find the concentration of hydroxide for trial 3. But I don't have a K constant. So I had to find my K constant first. And my K constant I'm getting as 699. Did you guys get 699 for your?
I have 700.
700. I may have forgotten to round. And it depends on which trial you used. I think I used trial 1. So, again, though, 700 and 699 were really close to that. Okay? Questions about what I did on E2?
You walk through the whole thing.
Okay. So, we're good on E1, though. Okay, just want to make sure. So, on E2, it asks for the value of hydroxide in trial 3. Then it tells me that the reaction is first order with respect to hydroxide. So, I now know that rate is equal to K times the concentration of S8 raised to the first. I just figured that part out. And then it tells me that hydroxide is first order as well. So if I want to find this guy right here for trial 3, I have the rate. I have S8 concentration, but I don't have K. So what I did is I picked either trial 1 or trial 2, where I have all of the information filled in the table. And that's going to leave me K, and I can solve for K. So that's what I'm doing right here. I manipulated my rate expression to solve for K. So again, this is just manipulated. The rate equals K times my concentrations. I plugged in my rate and I divided it by my 2 initial concentrations. The S8 was 0.1 and it was 0.01 for hydroxide. I just used trial 1. And I'm getting 699. And then now that I have K, check, 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 I can solve for hydroxide for trial 3. And so I put that in for trial 3. That making sense now? Okay. Just want to make sure. All right, so for F, it says using particle level reasoning. Okay, so if it specifies particle level reasoning. That means we need to talk about what's going on with the atoms and the molecules. Okay, so we need to talk about what's going on that level. And it says we need to provide two explanations that help account for the reaction rate being slower in trial 4. So there is no trial 4 on here, but the prompt up here talks about how we're going to conduct trial 4 on the next day. Right off the bat there, guys, what could be different the next day? The temperature, the pressure. We've got different lab conditions. And so, yeah, we're going to have different rates of reactions. Let's see what else it tells me. And it tells me that we have a lower temperature than yesterday. So I have a lower temperature. And what is going to happen as temperature decreases? What happens to the particles?
They stop colliding.
Yeah, there's fewer collisions. They're not going to stop totally, but they're going to be fewer collisions. And what else happens? Yep, we've got less kinetic energy. So that means fewer particles can reach their activation energy. So again, both of these are going to tell us that we're going to have fewer successful collisions. All right, so here we go. This is the energy profile diagram. Please hit pause and copy this down, and then I'm going to explain it. So our activated complex, that's a new term for us. This, you're going to love my definition. It's the blob. We talked earlier about how our reactants had to collide and stick together. That's the activated complex, the little blob that we end up getting. So this is the reactants when they stick together. Before they break up, okay? Into new products. And again, our enthalpy here, that is the heat at a constant pressure. And this is usually per mole. All right, so here's a reaction profile and rate. If we take a look here, we've got an EA that is lower. Okay. We've added something into this, and here's like our original OG. I can't spell. And then maybe this has something added in. In fact, we call those catalysts. If we've got a catalyst added in, a catalyst, if you've had biology, you're going to be familiar with the term enzyme. An enzyme is a biological catalyst. A catalyst is just anything that goes into the reaction at the beginning, and then it is given off at the end. and that catalyst is going to change the activation energy. Usually it's going to lower it. Sometimes it raises it, and those are called inhibitors. Okay, so an inhibitor is going to inhibit the rate of your reaction. But if I decrease the activation energy, what's going to happen to the rate? It's going to go up. It's going to be faster. So if I make it so I don't need as much startup capital, am I going to be able to have a successful business quicker? Yeah. It's not going to cost me as much. So another way to think of this, Olivia, is we've got these hills, right? Which one's easier to get over the hill? One or two. The lower activation energy. That means you're going to be able to do it faster. Okay. So we should have a faster rate if we lower the activation energy. We're making it so more molecules are probably going to have that amount of energy available. Okay, I just want to come down here real quick. Is this what I want to do? Okay, so it tells me that I have two reactions. They're represented above. We've got reaction 1 already in the diagram. Reaction 2 is endothermic, and the activation energy of reaction 1 is greater than that of reaction 2. So I need to complete this, okay? So they start me off right here for reaction 2. I'm going to do this in red. Which one has the greater activation energy, 1 or 2? 1, which means that my hill, has to be underneath reaction 1. Then it says, is reaction 2 endo or exothermic? Endo. That tells me I have to have my products above my reactants. And I guess I could put it over here if we wanted to. So that it lines up. And now I'm going to connect. Not much of a hump, huh? I didn't do a very good job of drawing that. But do you kind of get how we drew that? I picked I looked to see where would the products go, above or below the reactants, and then I looked at, is my peak higher or lower than the other peak? Okay. From the information given, determine which reaction initially proceeds at the faster rate under the same conditions of concentration, temperature, and reaction mechanism. Which one do you think is going to react faster? Reaction 2, even though reaction 1 is exothermic, we're going to see that reaction 2 is faster because it has a lower activation energy. And that is where I'm going to stop for today.